Start recording. Okay, well, welcome everyone to today's talk, Fluid Mechanics talk. It's a great pleasure to have with us one of our own, Yongyun Hwang from the Department of Aeronautics at Imperial College. Yongyun does all sorts of things, including some very nice work on turbulence that he's going to tell us about today. So Yongyun, all yours.
Thank you, Demetrius, and thank you also Peter, actually, both of you for actually letting me have the opportunity to present my recent work. It's always nice pleasure. It's always nice to be around this department. So today I'm going to talk about a bit more actually about the dynamic systems approach for multiscale state of turbulent flows. Okay, so the title is Multiscale Dynamics and State Space of Near Turbulence. So I'm going to start actually by introducing turbulence channel flow. Many of you quite know about this simple, very simple flow, which is actually kind of a model flow for all kind of boundary turbulent flows. So you can have other example, pipe flow, boundary layer, web flow, but basically they all share very similar properties. So the flow is actually coming from left and right like this, and then obviously the turbulent flow, turbulence is a multiscale phenomena. So here I'm going to introduce I'm going to start by talking with the two scales. One is actually the inner scale, which is typically important in the region very close to the wall, where the viscous effect on the flow become very important. So in this region, obviously the velocity scale, you can imagine it comes from the skin friction, which give you kind of the leading or the approximation of the velocity scale. And then also length scale also comes from the viscosity and the friction. So whenever I use this length scale, I'm going to put the plus symbol, and this is convention, and then many turbulence people actually use the plus symbol for that. Of course, if you move much farther from the wall, then you have actually your flow actually will be dominated by the inertial effect. In that case, obvious length scale is the half height of the channel H here, and then that one, and then in this regime, of course, as I said, the length is H, but I'm going to stick with the velocity scale U tau, which is still originate from the friction. The reason for me to consider the velocity scale even in the outer region with the U tau is because in the channel flow, if you consider your flow is actually driven by the pressure gradient, and then it's a statistically stationary, which means actually that the pressure gradient is directly balanced with the friction, and the pressure gradient is the only source of the energy source for this flow. So therefore, as long as you deal with the points of fluctuation scaling, etc., and then U tau is still, the friction velocity is still the one that you will want to use, okay? And the one quick point that I wanted to mention is that if you actually consider the ratio between the inner length scale and then the outer length scale, you will actually get the Reynolds number, which often we call a friction Reynolds number. And then this is actually just a ratio between the two. And then this is also a measure of actually how turbulent the flow actually is. So let me first start from this the general the structural organization of the flow. Okay, that was hypothesized by the Alan Townsend, roughly now half century ago, and there was actually a review paper by people at Melbourne, Ivan Mergic and Jason Monti. So it's easy to start from the mean velocity, because the mean shear is the source of the coherent structure or energy containing eddies or turbulence whatsoever. So if you consider the near wall region, obviously, as I said before, the most relevant length scale must be the viscous length scale. And then you can actually say that in this region, everything scales in inner unit that will give you the low of the wall like this. Okay. In the very far from the wall, you can have what is called velocity effect low. That was actually first derived by von Kalman, because at that, in 1930s, people often ignored actually the viscous effect on the turbulence, especially in the new wall region. So their equation of motion often start with the inviscid equation. Okay, so therefore, and then they try to generate the solution about the center line, and then this is how they come up with this law. And here UC plus is the center line velocity of the channel, which is actually also the part of the boundary condition in the original problem in the von Kalman. And then, of course, it was von Kalman who derived what is happening in the layer between the two, but his actually derivation is a bit dodgy, actually, although he derived this first. But actually, it was Millikan who actually derived that by matching this equation and that equation, and then he derived that in the layer between the two, you will get the famous Luglo, and with a constant kappa, which is called a common constant. Okay, that was a, I think, rather well understood story, because we teach this in our undergraduate for our undergraduate students. But the one thing that I'd like to point out quickly is that this Luglo is extremely robust. So this is actually the mean velocity profile obtained from Princeton superpipe, and this is the data from Sarabula Smith, and in 1997. This is the behavior of the mean velocity profile drawn in logarithmic Warner coordinate, and you see that the Luglo is extremely robust, even up to extremely high Reynolds number. So when you accept the Luglo, then you can actually have you can deduce the kind of eddy structures in the Luglo. That was exactly what Townsend did roughly half century ago, and that is called the attached eddy hypothesis. Okay, so if you consider new wall region, our mean shear is scale in inner unit, which means the coherent structure or the energy containing eddies coming from that shear must scale in inner unit. Okay, and then if you go to the outer region, you also have to consider the length of scale of the global shear, which is h. Therefore, you expect that the largest eddies in the channel flow should scale in h. Okay, so now in between, there is no length scale, but the most relevant length scale is distance from the wall, y, which actually also give you the Luglo with a simple dimensional argument. But what is happening is that in the Luglo layer, the length scale is the distance from the wall. For that region, the eddies, the energy containing eddies that you will see from the shear is supposed to be proportional to the distance from the eddy center to the wall. Okay, that's what Alan Townsend hypothesized in roughly half century ago, and then he actually did a bit more aggressive hypothesis, saying that each of the eddies actually could be similar. And then with that, he actually also make some prediction about the general behavior of the turbulent fluctuations. But about that, I'm not going to cover in this talk. But instead, I'm just actually give you this. I give you this explanation about the general eddy structures, and that was his hypothesis. During lockdown, I had some simple idea, and then I managed to prove this hypothesis mathematically in terms of energy balance. So if you are curious about this, actually, just check out this paper. So over the past 10 years, myself and my research group actually spent lots of time, made lots of effort to understand those dynamics of each attached eddies. And what we have found is this. So we had actually a nice numerical experiment in which we can actually isolate the eddies at single length scale using the overdamped large eddy simulations. I'm not going to explain you how you do it, but this is actually the dynamics we see from those numerical experiments. And then, so what we have done here is that we define this, and the Fox average is the streamwise velocity fluctuation, and then also define the Fox average the Voronoi velocity fluctuations. And then we just run the simulation, and then you will see that there is actually quasi-periodic oscillation going on. What is interesting is that there is actually very good the phase relation between the streamwise velocity fluctuation and Voronoi velocity fluctuations. So if you look at the fluid field, what is typically happening here is that there's a long structure here of the streamwise velocity, which is denoted by blue color here, and appears, and then we call that streaks for historical region. And then there is a Voronoi velocity fluctuation, which is actually denoted by the red isosurface. We'll call it rolls. And these are actually formed like this at when time equal to, say, at this point A, okay? So what is typically happening is that those rolls actually converted to the long and energetic streaky structures, and with a large energy amplification, of the streak energy. And those actually, the streaks actually begin to actually break down with the instability generated by the span-wide shear. So if you have a streaks and you typically experience a very large shear at the plank of the streaks, and then you get actually nicely formed waves, and this instability wave actually breaks the streaks strongly and then form the roll again. This is something that we found, but this process was known as a self-sustaining process that was actually discovered by some other people. Sorry, before going that, let me show you some movie, just in case you want to see what is happening. So this is a streamwise direction, and this is a spanwise direction. And here I'm plotting the contour of the streamwise velocity fluctuation at one cross-section y equal, say, over y equal 0.2. And the blue means actually the low speed region, which means actually negative streamwise velocity fluctuation. So let me play the movie. So what you see here is that it gets dark blue, which means it has been strongly amplified, and it become wavy, and then it disappeared, and again amplified, and the experience instability waves break down like that. It is repeated like this. So this process is not something that I actually discovered, because that was actually studied way before we found that, because that was actually something you see in low Reynolds number flow and China flow, so near the transitional regime. So this is what is called the self-sustaining process. That was actually all really in the context of turbulence. It was actually first proposed by Hamilton, Kim, Wolof, and then later Phil Hall and co-workers actually realized that that has some similarity to their earlier work. I'm going to mention that later. But this is a schematic diagram that you can see here, is that you have rolls here, and then that actually converted to streaks. And the streaks actually convert to waves with the instability, and the waves actually again regenerate to rolls. Okay, so that's the self-sustaining process. So there were actually some substantial development from these observations. This is something I'm going to actually tell you now, which is about the mathematical structure of self-sustaining process. So if you look at this actually process, you will see that streaks are typically elongated, and then in the small box, it's actually typically resolved by streamwise uniform streamwise Fourier mode. So the lambda is equal to infinity. But in the rolls and waves typically have the largest energy in the first wave component in the streamwise direction. Okay. Therefore, what you like to do typically is that you want to decompose it into streamwise average field and the rest. Okay. And then you write down the equation by decomposing into mean and streamwise average fluctuation and then rest. And then that first one, equation for U naught, give you the the equation for streaks. It's basically stream-order average velocity fluctuation equation. I'd like to mention that this particular bit, is actually globally stable. So it's always stable for the infinite Reynolds number. It never generates any instability mathematically. You can prove it quite straightforwardly. But you see that also it has actually driving term, which we call which actually we often call represent the Liptov effect, which is actually related to the conversion of the rolls to long streaks. This equation, as I said, globally stable, and it has a driving term, which is coming the rest of the variable, and you can write that equation in that way. That's the equation for rolls and waves, and you see that there is a production term here that is the source of the actual instability, which you see as waves. Okay. So these are the equations, but these actually dynamics sometimes allow equilibrium states. So what it means, actually, you can actually have steady solutions which are not laminar state. That has been called exact coherent state. That was first actually discovered by Masato Nagata back in 1990, and then Fabian Wolof actually computed that, and Bruno Eckart and Rich Curdwell also actually computed a lot especially for pipe flow earlier days. And then later, actually, Phil Hall actually realized that this is exactly identical to the theory he developed back in 1991. So in that theory, he considered exactly the same situation for compressible flow in the original paper. And then what they have done is that they ignore this nonlinear term and make this part as a linear, and then take the implicit limit and require the marginal stability of the Bill markers back in 1950, and then close the entire system. So that is this famous actually theory of the Phil Hall's vortex wave interaction theory. Okay, so these are the vortex wave interaction theory. What is nice is that it offers an analytic way to describe this exact coherent states. The other importance of this exact coherent state, especially from our dynamical systems view, is like this. So now let me consider what is called state space or phase portrait. So where this dot is actually represent the equilibrium solution of Navier-Stokes equation. Okay, so obviously you have one solution which represents the laminar flow, and there are many solutions you will see as you increase the Reynolds number. And in the typically at low Reynolds number, where the transitional Reynolds number, you only see, you don't see many solutions. And then the initial belief was that those solutions actually they are organized around the turbulent state. This is turbulent state, and the time trajectory of turbulent state, which appeared to randomly bump the other solutions. Of course, there are more advanced in this type of approach, especially with the computation of a periodic orbit. But let me just stick to this exact coherent state at this point, equilibrium states. And there are nice reviews earlier by Bruno Eckart and Genta Kawara, and then more recently by Mike Graham. So from that, what we have long suspected is that there must be exact coherent states which actually present each of the attached eddies. Okay, so we spent quite a long time to find one, and I was actually fortunate enough to work with the Oliver Young and then Ashley Willis actually, and then with them we managed to find the one solution in turbulent channel flow given in this form, and then you see that these solutions are all attached to the wall, and they seem to be similar, like you see the picture consistent with the tangent attached eddy hypothesis. Okay, and then the last year we also compute a lot more by making some more approximation to the equation of motion. So that was done by Patrick Duan and with Ashley again. Okay, so from there our superficial kind of the superficial understanding is that, okay, each of them has a self-sustaining process, and so therefore you have you expect to have a exact coherent state related to that, and then so therefore we thought, okay, this is good, so therefore we thought we understood almost everything. Okay, that was the story. But the next question is the really the challenging one, is that, so now we have exact coherent states for each of them. Then real question is, can each of those exact coherent states for individual attached eddy form a basis of the description of multiscale turbulence? This was the question that we asked with the Patrick Duan, and I think these are actually the really, especially Patrick Duan, actually they examined this very extensively, and then he did the most of the work by patiently actually coding lots of actually complicated observables. So obviously the pool system is going to be too complicated. It's more like fractal-like structure of the coherent structures. So what we wanted to do, we wanted to generate the kind of the dramatically reduced multiscale system. So what we wanted to do, we only wanted to consider two scales. Okay, so we had to design the numerical experiment in which we only have two scales. Okay, so what we have done is that to do this, we consider the equation of motion for turbulent channel flow. And the first equation is the equation for mean, and the other equation is the equation for fluctuations. Okay, and we will focus only on the near-wall region, so which means y plus is a finite value. But on the other hand, we also interested in very high Reynolds number. So what we are going to do, we're going to ignore this term by taking the large Reynolds number limit. Okay, then this is the equation of motion, and then to solve this equation, we generated following numerical set experiment. So this is actually a small box, okay, and then we chose the dimension in z and x and y direction by scaling in a unit, and we apply the uniform shear stress at the top. By doing so, we only create the linear shear flow, which immediately make us actually ignore this term, which is actually essentially coming from the pressure gradient in the Navier-Stokes equation. And then we considered the domain side, which is just large enough to host two scale coherent structure systems. So then if I quickly remind you about the side of the smallest actually coherent structures, the world turbulence is this one. Okay, so you see that span-wise side of the structures of roughly 110 or 100. So here we consider roughly 220. Okay, so these are the box size that we considered. So now we have to define the observables and we have to analyze this system. So what we have done is that we decompose the flow field into two. One is large scale, the other is a small scale. So the large scale only consider the structure related to span-wise wave number equal 1. So in this, the fundamental span-wise wave number. And then small scale covers the rest. Of course, this decomposition is not the best way to decompose the flow field. So there will be some problem with this later. But for the moment, let us just accept this decomposition, which was actually defined for a matter of convenience. Okay. And then what we have done, we write down the equation for UL and US. So this is the equation for the large scale. And then here, all the linear terms are actually remain the same. For the nonlinear term, we actually apply the projection operator to this nonlinear term. And also, we also wrote down the equation for small scale in an exactly same manner. And then we did something more sophisticated. So, and then what we did, we write down the scale by scale energy transport equation. So basically what we did, we multiplied UL to the first equation and integrate over the box, and we multiply US to this equation and integrate over the box. And then this is the equation, and this is the structure that you see, okay? So this is the streamwise energy of the large scale, or normal energy, and span-wise energy of large scale. And this is the streamoid and more normal and spanoid kinetic energy for the small scale. So if you look at this equation, the first term is actually the production term that derives all the coherent structures. Okay, so each scale has a production term, but they are only appearing in the streamoid component because of it, we are considering parallel flow. And the second term that you see is the intrascale nonlinear transport term. So basically the nonlinear term, which actually circulate energy around within the scale, but we found that this is not dramatically important term. So we're not going to discuss a lot with this term. But the third terms are quite important because they share exactly the same term both in the large scale and small scale. You see that large scale, this term appears with the minus sign, and then in the small scale, it appears the plus sign. So what it means, actually, these are the terms transferring energy between the two scales. Okay, so these are quite important. And third term is related to pressure. And the pressure term is also very important because the pressure, if you term is actually using the continuity, is satisfy this property. Okay, so the summation of the three components is always 0, and this has important physical implications because its role actually is in the distributing energy coming from streamoid direction to the other components. And then third term is viscous diffusion transport, which we are going to ignore because they are typically quite small. And the last final term is the dissipation term. As you imagine, then production and dissipation in this equation must be balanced. Like this. And also, we spend lots of time to compute the exact coherent states. Okay, so we managed to find roughly 28 exact states, 10 of which are large scale exact state, and 18 of which are small scale state. These are the actually 2 examples, and they all exist at the same domain. So we now had a great hope. We plotted the state space. Okay, so we just vaguely defined the amplitude of large scale streaks, which is defined here. It's just the energy of the streamoid unique component of the streamoid velocity, and this is small scale streaks. And then what you see here is that we have lots of dots here. These are the all indicating the exact coherent state in this phase portrait. And these actual gray cloud is actually the turbulent trajectory. And then Patrick run very, very long simulation. So we have a very dark cloud of turbulence here. So this is a small scale energy and large scale energy. And what you see here is that small scale energies are roughly bounded from here and here. And then the large scale energy are bounded by here and here. So if you superficially or vaguely assume that the turbulence are basically superposition of those two energy, what you see here is that the turbulent cloud is actually really well actually placed in this region. That was the first observation, which made us slightly happy. But that made us actually, we also checked the other variables. For instance, this wave of the large scale and wave of the small scale, which is a wavy component of the streamwise direction. And what you see here is that the same story does not actually go on for this particular variable. So we also examine all the other variables, and then we begin to have a doubt about our initial thought. So can you get coherent state for individual attached eddy really form a basis of multiscale turbulence? And then we are not sure about that. And then the question is, why do they not form the basis? So what we realized that there are lots of processes that were not actually dealt by the get coherent states that we computed. Okay, and then I'm going to introduce you to what those processes are. The first process we found is actually dissipation of turbulence. So, and this is actually typical, this is a schematic diagram, okay, very rough schematic diagram of the energy cascade, which is especially important for larger scale, okay? So, as I said, I'm going to ignore those terms which are not very important and which are not very strong. So what we found is that you have a production from large scale that coming in only for the streamwide components, and that production is balanced with the nonlinear transport in the streamwise direction, but it's also with the pressure strain term. So these two actually both are quite large, so it's difficult to say which one is more important. So what is happening is that these two balances the production for the streamwide component, and this one take the energy from production and send the two other components. Okay, and then this form the loop, which actually the distributing energy within the larger scale. And then the most of the energy goes to the small scale because the larger scale dissipations are weak. And then the small scale again does actually same business. And then what is happening then in this production and eventually go to a small scale dissipation, and then that actually described kind of energy cascade between this two scale system. But that was the observation. So what we have done is that we actually plot the base force rate of turbulent dissipation. So this is the largest scale dissipation, but especially for Warr-Newman and span-wide component, and this is a small scale dissipation and Warr-Newman and span-wide component. And what you see here is that most of the exact coherent states actually do not actually sit in the middle of the cloud, except this yellow one. The yellow one is actually a very special one, which I'm going to talk to you later on. So for the moment, I'm going to ignore it. Okay. So what you see here is that most of states do not sit near the turbulent cloud. We begin to realize something is actually wrong. Something's not wrong. So it's the exact coherent state do not have something that turbulence has. Okay. And the same is true. This pressure strain term, which actually plays a role of the redistribution of the energy. Okay. So in the exact coherent state, those pressure strain terms are considerably weaker than turbulent states. So what we realized that most of the exact coherent states have a problem with the turbulent dissipation. So this is the dissipation. So I just come up with a one particular solution. Sorry. So I have one solution. I just visualize the dissipation of the one exact coherent state here. Okay. So you see that the dissipation isosurface is highly anisotropic, and also it is elongated and also roughly quasi-2D. It doesn't have a full three-dimensional structure. And then also it is organized around the critical layer. Okay. On the other hand, in the turbulent state, this dissipation is a highly isotropic, even at this relatively the small degree of freedom system. And you see there are lots of structures actually more or less isotropic like this, with a lot more small structures. So, and we realized that by considering the mathematical equation that describes exact coherent state based on the Pelholz asymptotics, and we realized that the many exact coherent states, which are well described by this vortex wave interaction theory, which typically ignore this lost nonlinear term here, and then realize that that nonlinear term actually is related to in turbulent flow related to energy cascade. So therefore, the production dissipation balance is not with the in exact coherent state. It is actually based on this production and the critical dissipation created by the critical layer. But in turbulent flow, this production is balanced with the energy cascade. Okay. So that was the first problem that we found. The second thing is that there are also small scale production that is not captured by the exact coherent states. That is also driven by energy cascade. So exactly same schematic applies here. You still have a production send energy to the nonlinear and pressure strain components. And then you have an energy cascade to small scale. And then we realize that there are some situations where the small scale, especially the Warr-Newman component of the small scale actually activate the production at small scale. Okay, that was something I surprised when we saw this first time. So here, I'm going to focus on three variables. This is War-normal pressure strain and War-normal turbulent transport and small scale productions. And you simulate that, you check how they behave in time. And this is the plot that we obtained from DNS. And what you see here is that the small scale, this nonlinear transport given with the black line shows very strong correlation. It's a small scale production, but you see that it is not always correlated. For instance, at this point, the production is still large, but your nonlinear transport is quite small. This is where the small scale self-sustaining process generate the production. Okay, and if you actually compute the correlation, you will see that it actually has a quite good correlation. Okay, so then question is, what is happening? So we took the one particular part of the flow field, and this is the kind of movie that I wanted to show you. So these are the black line again is the linear transport given with the black isosurface here, and the green line is the pressure strain term, and then the red line is small scale production, and then here there's a red isosurface is also small scale production, and also the yellow one are actually small scale the velocity fluctuations. With the only wavy components, not the strict K components. And this is what you see from the movie. So what you see here, if you come in here, and then when the nonlinear transport begin to large, you see this dark structure here. That dark structure actually get amplified, and then it generates a large actually red structure with at the same spot, which is actually the turbulent production contour. And you see that large of turbulent production actually happen with this actually blue, the nonlinear transport, and then it generate additional energy in the streamwide velocity component. Okay. So then that's what is happening. Then what is going on with that particular fluctuation is this. If you actually check the side view of these fluctuations again, you will see that the large production takes place when those structures are actually given and they are gradually tilted downstream. Okay, this is the famous OR mechanism. Okay, so what is happening is that cascade generates a localized structure, and then the OR mechanism, which is related to tilting downstream of tilting of the vertical structure, which give you the transient amplification of the kinetic energy from this, and then that's actually the way that small scale production is enhanced by the energy cascade, and obviously a jet coherent state do not have that particular processes. Okay, the other thing that we discovered is that also there is actually inverse energy transfer from small to large scale. So in that case, we start from small scale production mechanism, which is not from the OR mechanism. That small scale production that we are going to study is primarily from the self-sustaining process at small scale. And that again is the similar story. It sends the energy to the nonlinear transport term and pressure strain. And then in this particular case, some of the energy, not all of them, not much of them, some of the energy, especially the energy distributed, especially in the near region, where the y plus is smaller than, say, roughly 20, send the energy to the larger scale. And then there is a balance at larger scale with the larger scale dissipation. So in that particular case, we found that this process is particularly important and stream-wise and the span-wide component. But here I'm going to focus on the stream-wide component. And then this component in the end actually generate energy for the large scale. And then also this transport term was also monitored and what is happening at the small scale self-sustaining process by monitoring the wave component of the small scale self-sustaining process. Okay. So this is again the time series of the small scale wave component, which measure the small scale string instability. And then this is the measurement of the nonlinear transport that we are focusing on. If this term is a positive, then there is energy transfer to larger scale. And then, we also consider the evolution of the large scale energy in the region close to the wall. Okay. And then what you see here is that all those streaks are fairly well correlated. So what it means is that when the small scale self-sustaining process shows instability or wave component, it actually generates also large energy some energy transfer from small to larger scale. And we call it fitting because it's not very dominant effect happening, you know, compared to energy cascade. So again, we check this part, and these are again the movie. Here you see that this orange line is about the wavy energy component of the small scale structure, so which represent the strength of the waves at the small scale, and or the instability or small scale. And we actually visualize only in the region very close to the wall here, y plus 0 to 30. And then the black line is the energy transport. As I said, if that is a positive, it will generate a inverse energy transfer from the small to large scale. And then we have the pink line that is actually related to the okay, it has to be pink line, sorry, to the strength of the large scale energy given fed by those actually large scale energy transport. So this is a movie. So what you see here is that when the wave component begin to intense at small scale, what is happening is that this dark actually ice surface, which is represented by this the nonlinear energy transport, they begin to be active, and this you see that the purple isosurface, which actually indicating the energy at large scale, and you see that the logical structure actually developed around those actually the positive energy transport to the larger scale. Okay. So what is nice is that you can also check the spatial structure of those actually events. So this is a one snapshot, this figure, one snapshot at y plus taken at y plus equal 8. This is a span-wise direction, and this is stream-wise direction. Here is the red is the high-speed region of the U stream-wise velocity fluctuation, and the blue is the negative region of the stream-wise velocity fluctuation. So this is actually small-scale streaks. Okay, and then what you see here is that this nonlinear transport is typically highly localized around this concave region between the two streaks. Okay. And then what we did, actually, we did the proper orthogonal decomposition with a snapshot taken on the plane. Of course, actually, we applied the periodic boundary condition and Z and X direction. Therefore, our POD modes are all Fourier modes. So what we did, and we actually considered several leading POD modes. So say here we consider 8 POD modes, but we can also consider many, but it didn't make any difference, even if we consider more. But this is the structure that we have seen here. So these are the low speed streaks here, the blue region. And then what you see here is that the positive part, which indicate the energy transfer from small to large scale, is appearing in the high speed region between the two streaks. And what is nice is that the streak actually shows this kind of nice ball shape. And then there is a concave region, which seems to generate intense the nonlinear energy transfer from the small to large scale. So that is actually related to the breakdown event of the streak in the self-sustaining process. If you consider two streamwise uniform streaking motion and you write down the numeric mode solution, which is given here in terms of a Proke mode. Here, let's say this is a mode that we are interested in, so string instability mode. And then this is the Proke, the numeric mode. And here, depending on the value of the epsilon, if the epsilon is 0, this is a fundamental mode, which is not generating any of the wave components. But if the epsilon equal to 0.5, it's a subharmonic mode. It can generate the mode, which is actually larger than the small scale structure. So in our previous POD analysis shows that that particular event is related to the subharmonic streak instability. You see that this is the low speed streak, the dark region, and you have this actually the convex region, convex region that is related to nonlinear transfer from small to large scale. So what was fortunate, I think that we actually managed to get one particular solution related to this feeding event. Okay, that is I don't know whether you remember now, but when we studied the phase 4 trait, there was one particular solution which does not seem to actually behave like the other solution. This is that solution. So this is again this low speed streaks, and then you see that they are actually like really see the structure related to subharmonic senior smooth instability, and then there is a dark region which indicate the nonlinear energy transfer from small to large scale, and that appears indeed and in the convex region of the high speed streaks. So you can check this particular state in the, again, this is the large scale wave component, and this is the nonlinear transfer term from small to large scale, and this is the phase state, phase 4 trait location in the these phase 4 trait. You will see that these guys indeed generate the energy transports from small to large, and then that is somewhere in the turbulent cloud. Okay, so you can now check the dissipation plot. This is a large scale dissipation and small scale dissipation. This particular solution actually is very close to turbulent cloud compared to any other solutions. So this one is a multiscale solution which seems to resemble turbulence most. And so we are a bit pleased, but if we also consider other types of the phase 4 trait, so here that we consider that same solutions, and now we check the energy of the large scale streak, and this is a small energy of a small scale streaks, and you see that this particular multiscale solution does not have any large scale streaks. And the same is happening for the large scale rolls and small scale roll space. It doesn't have any large scale rolls. What it means that multiscale behavior is entirely driven by the feeding event, and then this solution does not have the large scale self-sustaining process mechanism. Okay. So these are the 3 processes. We found actually that the exact coherent states actually are missing to capture. And then, but of course, then you will say that, oh, then you will have to compute the more sophisticated periodic invariant solutions such as the periodic orbits, right? So this is something that I'm going to talk for the next few minutes, and I'm going to conclude my talk. So remember we are in shear flow, and remember you consider small scale traveling wave solution, which is like say one exact coherent state or some state at small scale, and you have a large scale state. But because of the difference between the mean velocity for the small scale and large scale, what is generally expected is that the large scale state move faster than small scale state. So what it means in the moving frame of either of them, so let's say we are actually in the moving frame of the small scale state, and small scale state is equilibrium. But if you consider a multiscale state, which truly incorporate everything in turbulent flow, what is happening is that one for the large scale state is expected to have a faster speed than the small scale one. So therefore, what you expect is that the minimal form of the invariant solutions, multiscale invariant solution, which describe everything, is supposed to be periodic orbit, because this one is moving this is also period orbit in the moving frame of the small scale. This actually makes our life very complicated if you consider more multiscale, because if you consider 3 scale, then this structure, which is describe everything, should be 2 torus, which is extremely difficult to compute. Okay. Of course, there's one nice example. I'm not saying that this approach is it may not be really useful for multiscale turbulence, but actually, if the fluid is stationary, like the Rayleigh-Benard convection, you can actually compute. Although this is the only solution that I am aware at this moment, that one was computed by the Japanese group by Kenta Kawara, and these are the multiscale solution from the Rayleigh-Benard convection. As you see, that was just actually appearing in this year. It was not published because this is still in archive, if I understand well. Okay, so I'm going to conclude my talk now. So we ask, can really the eject coherent states for individual attached eddy form a basis of the multiscale turbulence? And then my current answer is probably not. But if you, I mean, any of you have a much better idea, then please do let me know. Okay, but I really appreciate that these can be used to understand the partial process of turbulence, not the entire process of turbulence, but by computing lots of them, we can understand the physical process that is actually can form local equilibrium. The other thing that we really learned, I think this is more valuable than the computation of the loss of eject coherent states. So that is this. So we had 2 self-sustaining process. So at large scale and small scale. Okay, this is a roll straight wave diagram. And then if you study turbulence, and then the most fundamental thing in turbulence is a production by the mean shear and dissipation. Okay, in shear flow turbulence. And what is actually happening is that the mean shear pumps the energy to this when each self-sustaining process convert rolls to streaks. This is what is known lift-off effect. This is where the turbulence production takes place. And when these streaks actually break down into wave and form rolls, it actually does an intense energy cascade and generate the fine scale structure and generate a large turbulent dissipation. That's the process that we identified. The other thing that we identified is that at the large scale, during the large scale self-sustaining process, the energy cascade, the structure-related energy cascade can be amplified by the Orr mechanism, and that it also takes the energy from the mean shear and also dissipate out. That's another production mechanism which I have not been aware for many years. And the last mechanism is that when the small scale structure breaks down, the wave, the particular arrangement of wave can actually pump the energy to the large scale self-sustaining process. Okay, these are the new process that we understood, and I'm going to stop my talk from here. Thank you for your attention.
Thank you very much, Yongyun, for a very interesting and illuminating talk on a very complex physical system. And we have several experts in the audience, so we'll open it to questions. Any questions, please unmute your mic and ask it, or you can put it in the chat if you want to, and I'll read them out.
Hi, Yongyun.
Hi.
Thanks for a very nice talk. I have a question about how you are, generating your guesses for these traveling waves. Like, is it possible that you missed some? You didn't have many multi-scale structures.
Yes, that is true. So number one, it was very difficult for us to compute directly from direct numerical simulations. So what we did, we actually go to single scale and we did the continuations from the small, from the system we had already single scale. So you're right that by doing so, we could have missed a lot of multi-scale solutions, but getting the multi-scale solution directly from the DNS flow field was found very difficult in practice.
Was that same reason for the restriction to traveling waves rather than periodic orbit?
Periodic orbits, as I said, yeah, I think so. But if you have a much better algorithm, you should try. But I think it's in general much harder. Also in a way, this multiscale system is actually the system with a larger Reynolds number. So it's a much more challenging to have the computing solution because of the growing Lyapunov exponents. So and then also, as I said, I am not the only one who tried to get the multiscale solution for shear flow. I also had the same discussion with Yenta Kawara, who actually tried something similar for web flow, and he said it was very hard. And so they understand why the reason that they don't get this is probably because of that. But I am definitely looking for a periodic orbit which can describe the multiscale solution. So if you want to do it, please let us know. So we are very happy to work with you. Okay.
Thanks.
Okay, may I ask a question? Well,
Yeah, Shusong, go ahead.
Clarification, really.
Shusong, we can't hear you very well.
Okay, so you talked about at the beginning you have this outer scale.
Yes.
And the wall scale. Then later on you have say multi-scale. So small and large. Okay, I can assume large is on the scale of the channel width.
Yes.
So the small, how small? You said twice of the wave number is small. So that's not a characteristic.
No, I think we didn't solve
when you talk about small, on what length kind of characteristic length scale you are talking about?
We haven't solved the poor channel, number one, for this one. So
yeah, that's another question. Okay, I thought you answered. You said you did the DNS, but if you did do DNS, the mean flow is not prescribed. You can't have linear shear.
No, it's not linear shear. It's a laminar solution. It's a linear shear.
Yeah, so this is for DNS, not the over diameter areas, right?
Yeah, this is a poor DNS.
Okay. So okay, back to my question. Okay, so when you talk about the large and the small, so how large, how small is there any kind of scale?
Yeah, small. In this particular setup, everything scales in viscous Moore unit, and then our small scale is the smallest eddy, lambda z plus 100, which is this famous actually structure by Klein et al. In 1967, and that's the smallest structure. And then the largest structure is something twice bigger than that. That is actually, and then we have only two scale, large and small, because we deliberately restrict the box size to be 220, which is just twice larger than the smallest scale structure.
I'm still, so you have larger scale, so the disparity, okay, the ratio is the Reynolds number, right?
So this, we don't have Reynolds number here now because this one takes the infinity. So we take this part out. So these are the governing equation. If you scale everything in a unit, the viscous term is order unity, and then there's no Reynolds number. The only control parameter you have is the box size.
But you are simulating channel flow.
Yes, but this is channel flow equation, and then we approximate in the limit of R tau infinity, and then this is the equation. And so we ignore that, and also we remove the outer part of the entire domain. We don't consider that at all.
So it's part of channel flow then?
Yes, part of channel flow, and it's not poor simulation.
Part of channel flow, then
we don't simulate the outer part.
Yeah, larger scale and small scale in the all normal direction, they do not live under the same roof, right? I mean, they live
in the same room, because the large scale structure tends to penetrate into the very deep in the neo region.
This is possibly a related question in the chat. If you look at that, Yongyun.
Okay.
I think Rich has a...
Okay, Rich.
Yeah.
Okay, every is multiscale in distribution. Yes, yes. So the multiscale means is that for the turbulent state. Yeah, you're right. So I think the most of solutions, for instance, let me just quickly. Yeah, so this one, for instance, this large scale state does not have any amplitude. I mean, it has a small amplitude for small scale, but it's negligibly small, very small. But that one, by construction, has a 0 large scale Fourier harmonic. So so it doesn't have any the contribution to the larger scales. You know, relate the span-wide wave number related to larger scale. Yeah, you're right. It can be confusing, but you can't really decompose actually precisely between small and large mathematically.
But I wonder,
Yes.
if you take your inner layer, sublayer,
Yes.
is there a residual velocity at the edge of that layer
Yes.
when you get to what you feel is the edge? And then is that residual velocity driving the outer flow or helping to drive it?
So
I'm thinking about an analogy with what's called steady streaming
yes,
years ago.
I'm
thinking just in those terms, is there a fluctuating velocity which in some sense is driving the outer flow?
in this particular case, I think that the major I don't think so in this particular case, but the eject coherent state that we have actually coming from the bulk of the orthonormal location, say they're above y plus greater than 70. But I do think that there might be some part of the eject coherent state that is affected by that streaming. So, but I don't know, which one is important. But in this bulk of the large scale structure is actually driven by the lift-off effect, I think.
Which effect?
The lift-off effect, which is the terminology that we use to describe the evolution, say this term. So this is the equation for the streaks.
Yes.
And
lift
then,
up. Yes. Okay.
Yes. Yes.
Any other questions?
Well, okay, so this may be related to Trevor's question, streaming. So you assume kind of periodic box. So you practically rule out this sideband.
Yes.
Effect. So if your position is modulated in space, so if you have two wave numbers close to each other, say larger wave number, they interact to generate a difference wave number. That
Yes.
would feed into the larger scales, right?
Yes.
And here you only require, so you because you have periodic box and you rely on this subharmonic.
Yes.
But in general, there is a more.
That is true. About that, yeah. I mean, of course, we have to examine much bigger box to see that, but what what is happening. So first of all, actually, when you do the streak instability analysis, and the usually subharmonic instability is actually second dominant than the fundamental. So probably this is one important thing. And the other modes actually can contribute to instability. So I think that might actually can be a mechanism to generate a bigger scale. But the intensity, if you really do the DNS, analyze the profile and check the turbulence energy budget, but that one is rather weak compared to that particular one.
Mm.
Okay.
Rich, you have a question?
Yeah, let me unmute myself. Hi, Yongyun. I really
Hi.
enjoyed your talk. You've done a hell of a lot of work here.
Yeah, that's what Patrick did. Yeah.
Yeah, well, Patrick's worked very hard. This diagram you've got on your overhead at the moment. So I'm thinking, is that co-ep flow driven by surface stress rather than imposed velocity of the top boundary?
It is true.
Otherwise, you're basically solving a low Reynolds number flow. I'm a bit confused here.
That is exactly the case. Yeah, you're right. We basically solve something very similar to co-ep flow. Top boundary condition is different. The one good thing for doing this is that it breaks the upper and lower part of the symmetry. So some of the coherent states are quite similar to what we found in channel flow, like the wall-attached coherent states.
Right.
Yeah.
Right. So you have no penetration of the top boundary.
No.
Right.
Yeah.
And the Reynolds, what's the Reynolds number you use here then? It's
So,
just to 1.
Yes, 1. Reynolds number is 1, and it is the box size that controls the kind of the extent of the hierarchy that we want to incorporate.
So if you were to make the box sort of scales order 1,
yes,
what would be the equivalent Reynolds number?
I think it would be roughly around Aritau 200, which means actually in channel flow, I think in the co-ep flow, it should be Reynolds number, say, roughly around 4,000 in co-ep flow. If you assume that the Reynolds number that I'm talking about is based on half height and then sliding velocity of the upper wall or something like that.
Oh, I see.
Like
So how did you find your traveling waves in the first place then at 4,000?
So what we did, we basically went to much lower Reynolds number, which means actually we actually reduced the box size to be like minimal unit, and then we found a hell of a lot. And then when we put them, and then we actually doubled the box size at every direction, and then put them at the exactly 4 copies, and then continued to compute the small scale state. And the larger scale state, we just continued.
So how do you know you've got any upper branch states? It sounds like you've got lower branch states.
Yeah.
Is that what you have, lower branch?
Yeah, we do have a lower branch, lots of lower branch too.
Well, that's key, right? Because you imagine it's the upper branch, leaving aside the issue about periodic orbits.
Yeah.
Just considering equilibria or traveling waves, you really imagine it's the upper branch solutions that have the more complicated dynamics.
Yes, that's right.
Okay.
Yeah. So, but we have lots of upper branch states. Like I said, I mean, we have both upper and lower branch states.
Oh, so, you do?
Yeah, I do have a lot.
Oh, so how did you find the upper branch states?
I think Patrick patiently continued.
Oh wow! What, in span-wise or something?
Yeah, Patrick, can you unmute yourself? And how many upper branch states we have for the larger scale?
So in total, I think we have 3 or 4 upper branch solutions. Only 1 or 2 of them are somewhat close to the turbulent trajectory in the phase portraits. Some of them are still quite close to the lower branch, so that there's not much difference between the lower and upper branches. But there are a few upper branches as well, but even these fail to capture many of the characteristics of the 2-scale system and 2-scale turbulence.
Right. Okay, thank you.
Thank you, Rick. Yeah.
Great. I think Ellie Johnston has a question.
Yeah, I might have misunderstood this, but do the exact coherent states for the attached eddies exhibit any of the self-similarity of the attached eddies themselves?
Yes, yeah, they do. So, yeah.
Oh, sorry, you put it on there. Okay, no.
Yes. Yeah. Yes.
Right, cheers.
Okay, thank you. And any other questions? Well, if not, let's thank Yongyun again for an incredibly interesting talk. Thanks again, Yongyun.
Thank you, Demetrius.